Hopefully you will you'll manage no problem, and if not, just let me know if there are references. If you see there are references to chapter one or references to things that you go like, what is that? um, there's a chance it talks about chapter one, and then I'll let you know. There are a couple of problems that mention this. I think I've taken care of this in the answers to even problems document. I'm not sure, but it could be there. In any case, let's start chapter one, which deals with logic and proofs. So here's a little introduction to what this is all about. So logic is the basis of all mathematics reasoning, and all automated reasoning. And what we're going to look at more precisely is part of what's called symbolic logic, which is, I mean, the idea behind it is to create a calculus of reasoning, to have an algebra of reasoning. That would be the idea behind symbolic logic, which has worked up to a certain point, but that's a long story. I'll try to mention a few things here and there once in a while that go beyond the course, but it's a super interesting topic, especially if you're interested in computer science and the history of and machines and so on. Um, so the machines actually were first designed by logicians, by mathematicians doing logic. Um, you may have heard of the name Alan Turing. He's one of the main players in this story. Um, so and logic has applications at many different levels in math and computer science. So at the very basic level, the actual design of machines, it's logic circuits. So these are circuits basically built to do logic, and we're going to see that very soon. You may have heard things such as system specifications. Logic is used there. Temporal logic is a kind of logic that's used quite a bit in artificial intelligence. Obviously, programming languages, any decent programming language has a logic component. And I mentioned descriptive complexity. I've talked about this P versus NP problem, although I didn't go into the details. I'll try to go as we go along. But descriptive complexity is one of the possible lines of attack of this fundamental open problem, and it uses logic also. So it works at very many different levels. Okay. So here's an outline of what we're going to do in chapter one. As you can see, I'm not going to cover every single section of chapter one. I'm skipping 1.2. There might be stuff after 1.8, I'm not sure. That's in the book, but this is what I'm going to cover. We're going to start with propositional calculus, which is actually pretty straightforward. Propositional equivalences, I'll try to cover this today. I think I can cover both these sections today. Um, and then we're going to start adding stuff to our logic, which are quantifiers, which is going to make it a lot more interesting. And then the rest of the chapter will be dealing with these quantifiers. Um, the last two sections, 1.7, 1.8, are more applied logic in the sense that we're going to work on proofs, mathematical proofs. Okay. Which will be our tools for the rest of the semester also. Okay. All right. So let's start with some very basic things. So propositional calculus or propositional logic, we want to deal with things that are called propositions. So what's a proposition? It's a declarative sentence which is either true or false. You can also think of this as you may have seen this when programming, as a Boolean variable. So it's a variable that can take on two values, possibly true or false. Okay. But to illustrate all of this, we often use natural language examples, which can help and sometimes can be a little confusing. And I'll try to make that clear as we go along. A lot of the exercises I mean, there are a lot of exercises that deal with natural language examples, but I try to choose those where there's no ambiguity. The problem with natural language is there's bound to be some ambiguity at some point. Hopefully the exercises I chose should be free of ambiguity. So here are some examples of propositions. So these are statements or sentences which are either true or false. Toronto is the capital of Alberta. This is either true or false. It happens to be false. 1 + 1 = 2. This is a proposition and it happens to be true. All men are mortal. I mean, the study of logic goes back to the ancient Greeks, and this was a famous example that's been used for the last 2,000 years about Socrates and all men being mortal. But anyway, I'm sure you'll see it in the exercise at some point. And another one, some birds cannot fly, which seems to me that's true. Here's some examples of things that are not propositions, which might help even more than examples of propositions. What time is it? That's a question. It's neither true nor false. So it's not a declarative sentence. Read this carefully. This is an injunction, an order. It's not a proposition. The next two are much more interesting. So x + 1 = 2. You'll agree, I'm sure, that it's not clear if this is true or false. It depends on something, right? It depends on the value of x. If x is 1, this is true. And if x is not 1, this is false. So it's not a proposition by itself, but it's sort of close to a proposition. And in section 1.4, we'll start looking at things like that, where we'll modify expressions like this to make them into propositions. The very last one is even less a proposition in a sense. X squared minus 4x + 2. There's not even an equal sign, right? So it's just an expression, a number perhaps. If x has a value, this could be a number, or you can see it as a polynomial, but it's certainly not something that has a true or false value. Okay. All right. Now, what is absolutely wonderful is when you start, I don't know if it's wonderful, but at least I like things which are simple. It turns out that in math, there are very few I mean, the shape of a typical proposition is very simple. It's either this is equal to that, or this is an element of that. Essentially, all propositions in mathematics are of this form, basic, actually, atomic propositions. Again, when we start talking about quantifiers, we'll make that a little more complicated. But the very basic minimal propositions that you deal with in mathematics are of these form. Either two things are equal, or this thing is an element of that set. That basically all of math is built around propositions of this form. Okay, so of course, if you play only with propositions like this, it's not going to get deep very quickly. So you want to build propositions around these basic propositions, which are called compound propositions. How do we do that? We have connectives, like operations on propositions, to make some bigger propositions out of the smaller ones, the basic ones. Okay. To talk about this, I will use Boolean or propositional variables, which are, again, as I said earlier, variables that can either can take the value true or false. Okay, so let's take a look at our first connective. It doesn't connect two things. It's still called a connective, but view it as an operation on propositions. So you start with a proposition P, and you create a new proposition, which is called the negation of P. The notation right there is standard. That's read not P. Sorry, that was too hot. So the not P is the statement, it is not the case that P. Okay. Now to define this properly, I have to tell you what the truth value of this new proposition is in terms of the original truth value of the proposition P. So what we use is what we call the truth table. So you list all the possible truth values for P, that's true or false, right? And I'm going to tell you what the truth value of not P is in terms of those. And as you could very well guess, the negation just flips the truth value, right? So if P was true, then not P is false. And if P was false, then not P is true, right? And we have an example here in natural language. The statement P is Bob's PC runs Linux. So the negation of P is Bob's PC does not run Linux, okay? So I think that's pretty straightforward. Okay, let's take a look now at an actual connective that connects two things. So we now have two propositions, P and Q, and we're going to build a new proposition from those two, which is called the conjunction. The notation is it looks like intersection, right? And it's not a coincidence. There's a reason for that. This is read P and Q. And this is the proposition which is true exactly when both P and Q are true. So to define this properly, I show you the truth table. Okay, so here we go with the truth table. So what are the possible values, truth values or values for P and Q? They both can be either true or false. So that's going to give us four possibilities, right? True, 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 false, false, true, false, false. I'll get back to that in the next set of slides that I already uploaded when I'm talking about octal and hex and binary. I have a little section in there talking about truth tables. I'll get to that, maybe not today. I am not sure I'll get to it today. In any case, so P and Q is the conjunction of P and Q. So it is true. As you can see, this is the definition. So it is the P and Q is true when both P and Q are true, and otherwise it is false. Okay. So there's an example there in natural language. So statement P is Bob's PC runs Linux. Statement Q is Claire is tall. So the conjunction of these two statements is Bob's PC runs Linux and Claire is tall. This will be true if Bob's PC runs Linux is true and Claire is actually tall. Notice immediately, by the way, when we're talking about natural language, Claire is tall. If tall is not defined, then this is not really a proposition, right? We have to have a precise definition of what tall is, but that's another story. So I'm not going to do philosophical logic here. That's not my cup of tea. Okay, so things will always be extremely clear when I give you problems. Don't worry, okay? Next connective on our list, so we have negation, we have conjunction, and we have disjunction. Again, connective that connects two propositions, P and Q. It is read P or Q. It looks like union. There's a reason for that. It is an analog of union. So P or Q, this is the proposition which is true when at least one of P or Q is true. So now here we are starting to get into a more dangerous zone. If you start thinking in terms of natural language, the or in natural language more often than not is not this disjunction, but rather the exclusive or. So you have to be, we'll talk about that a little later, but you have to be careful with that. But here it's important. So the disjunction, the standard disjunction in logic, mathematical logic, is not exclusive. So P or Q is true as long as one of P or Q is true. If both are true, it's true. Okay. As you can see from the truth table definition there. Okay. So the only way it is false is when both P and Q are false. And I give an example in natural language, and notice that the last sentence, although, I mean, we're talking about a PC running Linux and the height of somebody in the same sentence, it's sort of a bit weird. But in natural language, often or means either that, but not both. Okay, which is not the case here. Okay, so we have now three logical connectives. One which is unary, it just takes as input one proposition. The other two are binary, they take two propositions as input. And what's remarkable is that these three connectives are enough to build whatever you want. Okay, in propositional logic, that's all you need. In a sense, you can build a computer out of three little circuits. If you can replicate them as many times as you wish, you can build any machine using only these three guys, if you have enough of each of them. Okay. I'm going to show you this. It's actually, if you see, it's what I here I'm talking about completeness of or, and not. I will show you why this is true, because the argument is not super difficult. And it's like really cool to think that everything can be written only in terms of these three things. However, as you can probably guess, if you write everything in terms of only these three guys, you might get expressions which are just really too nasty to handle, just too big. So even though in theory that's all we need, it's convenient to have other connectives once in a while, which are not one of these three. So I'm going to tell you about three more, which are the exclusive or, the implication or conditional, and the biconditional. Okay. The last two, implication, biconditional, especially implication, is really fundamental in mathematical reasoning. It's really, really important. Implication is like, it's really, when you're working doing math, you're using implication like 1,000 times a day. Okay, so that's it's really important to get it down clear and obvious. It might take a little while, but you'll get there. Okay, so let's start with the exclusive or, also known as XOR. And it looks like a plus, right, with the circle around it. And this is, as the name indicates, the exclusive or. It's just like an or. So P XOR Q is true when P or Q is true, but not both. Okay, so if you look at the table there, you see that it is true precisely when P or Q is true, but not the other. Okay, so exclusive or, as the name says. So we define this this object, this beast, this way because we feel like it, because it's useful. Okay, and so okay, so that's the exclusive or. Let's now define the condition. I'm going to spend a little bit more time on the conditional. I'll get back to the exclusive or when we're going to talk in a few minutes. We're going to talk about interpreting these connectives rather than seeing them as operations on propositions that are true or false. I'll see them as operations on variables which take on 0, 1 values, and then you can reinterpret things in a slightly different way. Okay, the conditional. This is like super important and perhaps not as familiar as everything we saw up to now. So I have two propositions, P and Q, and I create a new proposition, the conditional, which is read. There are many ways of reading this. The standard ways are if P, then Q, or another way to say it is P implies Q. And it has the following very strange looking truth table. So if P then Q is almost always true. It's false only in one instance, is that's when P is true and Q is false. Okay, I'm going to spend a couple of slides discussing this. Here are some words that you might see pop up here and there, especially in terms of math reasoning. So P is called the hypothesis of this conditional, and Q is the conclusion. You might also see the following way of saying this, which I mean, okay, I'm recording, I shouldn't say this, but what the hell. I still have to think about it once in a while. I mean, it's not like immediate for me. P is sufficient for Q, Q is necessary for P. If I'm working and somebody says, oh, this is necessary, sufficient, it'll take like half a second. I have, oh yeah, okay, this direction. Okay, so if it takes you a while, don't worry. I've been doing this a long time, and you know, it's not immediate. Okay, so I will not use sufficiency and necessary very much for that reason. Okay, but P implies Q, and if P then Q, these are standard, and I will use that obviously. Okay, so let's try to understand what the point of this conditional is. Okay, so what's the intuition? Okay, there are a couple of ways of seeing this. The fundamental thing, let's go back here to this. This thing is almost always true, and it's false only when P is true and Q is false. I have a hypothesis and I have a conclusion, and I have the truth value associated to the statement if P then Q. Okay, so notice first of all that if P is false, then whatever Q is, the implication is always true. So the bottom half of that table, okay, you see that if P is false, Q can be whatever you want. The conclusion here, I mean, the truth value of the conditional is true. So the intuition is this, is that from a false hypothesis, it is correct reasoning to deduce anything, okay? So if pigs can fly, then anything goes. Okay, so that's the idea. So so if 0 is equal to 1, then 5 equals to 17. This statement in itself is a true statement. I'm not making an error in saying that if 0 is equal to 1, then 5 is equal to 17. Okay. Now, if the hypothesis is true and the conclusion is true, then if P then Q is true, that's sort of natural, right? So the only one left is if P then Q, when is that case where it is false, that's when P is true and Q is false. So if I start with something, a hypothesis which is true, and I deduce something false, this is wrong logic, right? That's the way I see it. So if 1 plus 1 equals to 2, then 5 equals to 17. This is not correct, okay? This is a false statement, okay? So that's one way of seeing this, okay? But I think the fundamental thing is to think if you have a false hypothesis, you can conclude anything and it is correct reasoning. I think that's the best way to see it. Here's another way of seeing it, and I modified slightly an example from the book, and I'm very happy to say that it's not relevant anymore, but it was relevant last year and the year before, but it's not relevant anymore. But anyway, so consider the statement made by somebody called Donald, and Donald said or says, "If I am elected, then I will build a wall." Okay, so this is the statement that Donald is making. Okay, so let's try to see if this statement is true or false, depending on what happens. Okay, so if Donald is elected and builds a wall, then he told the truth, right? He said, if I'm elected, I will build a wall, so it's true. Okay, so if the hypothesis is true and the conclusion is true, then the whole thing is true. Now, if Donald is elected and doesn't build a wall, then he lied, right? So if the hypothesis is true and the conclusion is false, if I am elected, then I will build a wall. If he's elected, does not build a wall, then he lied. And now that what's the other possibility is that Donald's not elected at all. So do we consider that Donald lied by saying, if I am elected, then I will build a wall? If he's not elected, then we can't say that he lied, right? So that's, I mean, this is an image, right, to maybe help you remember the truth values of the conditional. That might help, okay? Hopefully that sort of makes sense, and that's easier maybe to remember. But anyway, so we'll play with this enough, hopefully, that you get used to it. Okay. Biconditional. That's our last one for 1.1. So the biconditional is actually easy. It is read if and only if, P if and only if Q. And if you look at the truth table just a few seconds, you will notice that this new proposition, the biconditional, is true when P and Q are true or P and Q are false. In other words, if they are equal. So P, if and only if Q, lights up true if P and Q are equal. That's one way of seeing it. Okay, so that's a useful connective. Okay, we'll see these a bit more. These last two, we'll see them a bit more when we talk about math proofs. Okay, yeah, about notation. Just like in arithmetic, in algebra, we have some conventions to avoid bracketing too much. So the convention is that negation has the highest precedence over everything. Okay, so if you see something like this, not P and Q, it does not mean not P and Q. The negation applies first, so it's not P and Q. If I wanted to negate P and Q, I would put brackets over here. Okay, so this is important to know, useful. Okay. So that's the order of connective, precedence of connectives. Okay. 1.3, propositional equivalence. Okay, so basically I'm going to give you a couple of definitions, and verifying these definitions is easy. Okay, you will see there's a very simple algorithm, not efficient, but for small propositions, that's fine, to verify the definitions. And then I'll tell you about the completeness of when I said earlier that the three basic connectives can generate everything. It has to do with this logical equivalence. Okay. Okay. So two compound propositions are said to be logically equivalent if they have exactly the same truth table. Okay. And the notation to say that two compound propositions, let's say they're called P and Q. I know that earlier I used P and Q as variables, but they could represent compound propositions also. So we write P equivalent to Q. It's like an equality, but with three horizontal lines. Okay. Here's a very simple, obvious example, but I think it's simple enough and straightforward enough to illustrate precisely what we want to do here. If you look at the negation of P, then intuitively you'd think, yeah, not P, right? That's the same as P, right? And by definition, it is, right? So if P is true, not P is false. And if I negate that a second time, it comes back to true. If I start with false, negation is true, negation of that is false. So you see that the truth values of not P are exactly the same as the truth values of P. So these two expressions, these two compound propositions are logically equivalent. Okay, well, maybe that's just too simple. Let's take a look at, wait. I want to do this, but I need to tell you how to build the truth tables. Yeah, so, okay. Obviously, if I give you two compound propositions, loads of variables in them, and I ask you, are they logically equivalent? So you look up the definition, say, okay, logically equivalent means that they have the same truth table. So how do you check that? Well, you build the truth table, right? So you just generate the truth tables, compare, are they the same? Yes, that's it, okay? So there's a straightforward algorithm to do this. If the compound propositions are very big, this could take a long time, but still you can answer the question, okay? If you have enough time. So how do we build these truth tables, let's say by hand? One useful way is to build smaller parts first. For example, if I have the compound proposition P or not Q, okay, so first of all, you notice that there are two variables. You have to think now, if there are two variables, there are 4 rows to that truth table, because I have 2 values possible for P, 2 values possible for Q. Again, combinations, that's 4, okay? I will get back to that about building bigger truth tables when I talk about binary. Maybe I should do it later today. We'll see. So I have my 4 possible pairs of values for P and Q: true, 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 false, false, true, false, false. I can then compute first not Q, right? It's a component in my compound proposition, P or not Q. And then I can compute the OR of P and not Q. So the OR, again, if you remember, OR lights up as true as long as one of the two is true. So true or false is true, true or true is true, false or false is false, false or true is true. Okay. So this is the truth table. If I erase this column here, I'll get the truth table for P or not Q. Okay. All right. How about this one? Okay, so here's a more complicated compound proposition. P or not Q, all that implies P and Q. So I want to know what the truth table of this thing is. Okay, so what is the truth table? Is a combination of all possible values for P and Q and the resulting value for the compound proposition. Okay, so I write my 4 possibilities for P and Q. There are 2 variables involved, so that's 4 rows. Okay. And then you see what I did here is I built these intermediate columns to evaluate the components of this compound proposition, right? So you have to recognize, you're parsing this, you have to recognize that to evaluate this, it's the implication you need to evaluate, which means that you need to know the truth values of what we call the hypothesis and conclusion, right? So I have to evaluate P or not Q first, and then P and Q. Once I have those two truth values, then I can evaluate the implication. Okay, so this is what I did here. If you look at these 2 columns, it's what I did previous slide. Okay, so P or not Q gives me true, true, false, true. P and Q, this is just applying the definition of and directly, right? So recall that and is true if both are true. So true and all these false. And then I evaluate the implication with these 2 columns. This is my hypothesis. This is my conclusion. And now I try to remember this. So how does implication go? As long as, so if the hypothesis is false, I have no problem. So I have false here, so this will be true. The only bad case, is when the hypothesis is true, conclusion is false. True, false, true, false. These are false. Otherwise, it's true. Okay. So the truth table of this compound proposition, you would, in theory, you would erase these 3 columns, and that's your truth table, right? It consists of these 4 rows here, these values for P and Q, and the values here. Okay. Now, sorry, I gave you the definition of logical equivalence, but I haven't been talking about it except for that simple example. I'm just showing you how to build the tables first. Once you know how to build tables, then of course you can talk about equivalence. Okay. So, all right. So here's finally an example of logical equivalence. So the it turns out, so okay, so this illustrates one of the things that I was telling you a bit. No. So you see this expression here, P, X, or Q. This is something we defined earlier, right? So we defined P, X, or Q as the exclusive OR, which you look at the last column. This is how we defined it. The right-hand side here, this is an expression involving only or, and not. And I'm showing you that, in fact, the XOR can be expressed only in terms of or, and not. Okay, that's what I meant by, if you take any truth table whatsoever, you can find an expression involving or, and not that will give you that truth table. Okay, so here this is an illustration of this for XOR. So how do I check that? Well, I build the truth table of this expression, which is not quite the same one as I did earlier. Okay, so let's see. I have an OR. I need to know the truth values of both of these smaller propositions in terms of P and Q, right? Again, there are two variables, so for rows, I evaluate not P and Q. I could have done a special column just for not P to start with. I could have done that, but I didn't. I would have run out of space, I guess, in my slide. But, and I'll show you, yeah, so it's not in the slides, but on, I guess on Thursday, I'll be doing more solving problems. And I'll show you a slightly different way of doing these tables, which is maybe a little quicker. If you're just looking to compute, you know, but in any case, so not P and Q, I compute in terms of these. Imagine the negation of P being pre-computed here. You do the and, this is what you will get. P and not Q, this is what you will get. And then you take the or. Okay, so what's the or? It'll light up as true as long as one of these two is true. So the middle two ones will be true, and that's it. Okay. Sorry, this is not the best on slides, I have to say, without the board. But so on Thursday I'll do some problem solving, and we'll get our hands dirty. Any questions up to this point?
Well, it's more about the course, but you said you're gonna do things on Thursday. Are still having a synchronous class tomorrow?
Yeah, sure. So yeah, tomorrow is a lecture. Oh, I said, yeah. Is that your question? Oh, no, I mean, did you say asynchronous or synchronous? Live. Tomorrow's live.
Okay.
Yeah. Direct from Greenfield Park. Live from Greenfield Park. It's the Discrete Math Show starring soy sauce. Okay, sorry. COVID is getting to me. I didn't catch it, I think, but being cooped up like that is. Yeah, I know. It's just that I tried that, and it's really like, it's really hard. But I'll check it out. Thanks for the I might try that. Um, okay, let's see. Okay, so the next thing would be to verify these fundamental equivalences. So basically, what I'm doing here is showing you that the by implication can be expressed in terms of implication and implication can be expressed in terms of or and not. This is a really fundamental one to understand. I mean, if you understand that, then you understand implication. And here's another one for the XOR. Although this one is really, it's, if you think about it, just a few seconds, it's pretty quick. Um, But I'll let you try those out by yourselves at some point. Okay. Um, I think that. Oh yeah. Okay. So I let's talk about tautologies. It's just this is it looks really silly as a definition. You might, I mean, many of you might go like, yeah, so what's the point of such a compound proposition? So a compound proposition is called a tautology if it is always true. Okay. For any values of the variable. So whatever values you put for the variables, the output will always be true. So it looks like what's the point? But there is a point. I'm not sure if I'm going to be able to make that point. I hope it's a bit technical, but okay. I hope I can sort of convince you this is important. So here's an example of a compound proposition, which is a tautology. P or not P. This is a tautology. This is always true. Whatever the value of P is, P or not P is a tautology. So basically what this says in terms of reasoning, if you wish, is that either a statement is true or it is false. That's basically what this says, right? So that's a very simple, straightforward example, and you can compute it, right? You can actually compute it without trying to interpret it in terms of reasoning or anything like that. It's just basic, just definitions. You apply the definitions, and you see that this column of truth values, it's all true, right? But there's a meaning behind it, which is interesting. Okay, here is another one, which is not as obvious. Okay, what Q implies P or not P. Okay, this is a tautology. Why is that? Well, you can compute it, or you can think about it in the following way. You said, okay, we just saw that P or not P is always true. Whatever the value of P is, this is always true. Okay. Now, an implication, how can an implication be false? There's only one way it can be false, is if Q is true and this is false. And this is not going to happen, right? So this is always true. But you can just simply also compute the truth table and you see that it's always true. Okay. So in itself, this looks like a very, very useless thing. But the important thing is that it's the expression that you're looking at. The fact that it's a tautology means something about the connectives and the way they're connected, the way they are put together. Okay, so let's try to clarify this. Okay, so there's a link between logical equivalence and tautologies, which is the following. Okay, so here's a theorem. So a theorem, we'll see that a little later, but a theorem, you've seen obviously you've seen the term before. It means a statement we know is true, okay, or has been proved. So our theorem here is that if two compound propositions P and Q are given, they are logically equivalent, meaning they have the same truth table, right? Precisely when the statement P if and only if Q is a tautology. These mean exactly the same thing. So you can talk about logical equivalence, or you can talk about tautology. You're talking about, in a sense, the same thing. If you're trying to verify, okay, let me little aside, but this is the part which is hard to I mean, it's hard to explain. At the beginning of the 20th century, the logicians, the mathematical logicians, were trying to set up, I mean, the holy grail was, could we build a calculus for all of math? Could we build a language in algebra that we could just compute with, and that would just do all the math that we want to do? Is there such a thing? Let's try to do it, right? And and one of the problems related to that was looking for tautologies and logical equivalents. In this setting, it worked well. So there is an algorithm, a machine. I mean, you're going to say, wait, there weren't any machines doing computations at the beginning of the 20th century, but mathematicians were actually thinking about that before they could build the machines. So one of the questions was, is there an algorithm to verify if things are a tautology or logically equivalent? The answer in this context of propositional calculus is yes. The algorithm is clear, truth table. That's all you have to do. When we get to the problem with this logic is that it's very primitive. It won't do all that you want to do in math. So you have to add more stuff. Once you add this stuff that we're going to see next week, do you still have an algorithm to check that things are logically equivalent or tautologies? And that's when the answer that Turing gave is that no, there is no algorithm to do that. And that's like where the interesting stuff starts to happen. But there's like a whole big story under here that I can't really tell you at this point, but that's the idea. Okay. So logically equivalent statements, tautologies in this little baby context of propositional calculus, they're sort of easy to handle. Once we move out of this baby logic, they're much harder to handle. Okay, that's another story. But let's get back to our little theorem. So why is this true? We want to verify, to understand that two compound propositions are logically equivalent, meaning they have the same table, exactly when the statement P if and only if Q is a tautology. Okay. Now recall that P if and only if Q lights up as true when P and Q are equal, right? So P if and only if Q lights up as true when P and Q have the same value. So to say that P if and only if Q is a tautology means that it lights up true all the time. And it lights up true all the time means that P and Q are always equal, hence logically equivalent. Okay, so that's the proof. Okay, hopefully my waving hands like this and talking is sufficient for you to understand. Yes, okay. Okay, all right. So that's the connection between tautologies and logical equivalence. Okay. Yeah, this is important. A lot of stupid things that you read on the internet have to do with people having trouble with these two things. That's another story. Okay. So this is something that is extremely useful, and it's like everyday stuff. When you're doing proofs, you're talking about converse and contrapositive of a conditional statement. Okay, so here's my definition. These are names for special kinds of propositions. So our base proposition is the conditional if P then Q. Okay, the converse of this proposition is you flip if Q then P. That's what we call the converse. Okay, the contrapositive of if P then Q is you flip, but you negate both. So if P then Q, the contrapositive is if not Q, then not P. Now you might ask, why consider such a weird looking thing? Because it turns out it is exactly the same thing as if P then Q. Okay, so they are logically equivalent. They mean exactly the same thing. However, the converse is not the same thing as the original proposition. I would like to illustrate this This is important. This is not only important for this course, it's important for daily life. Okay, so let's look at the illustration in natural language. If an animal is a bat, then it is a mammal. So if you didn't know that a bat is a mammal, then of course this is a bad example. But I suppose that all of you know that a bat is a mammal. It's a flying mouse, okay? So the mouse part is a mammal. So if an animal is a bat, then it is a mammal, okay? Now, the contrapositive of this, so what I do is I flip hypothesis and conclusion and I negate both. And I get, if an animal is not a mammal, then it is not a bat. I am pretty sure that you agree with this statement if you agree with the first statement and vice versa, right? So that's an illustration of, I mean, you can just compute that the contrapositive is logically equivalent to the original here, if P then Q, okay? But hopefully the high level meaning of this is correct for you. Now, to illustrate that the converse is not logically equivalent to the original, look now at this. If an animal is a bat, then it is a mammal. So we all agree on this. Now let's look at the converse. The converse is if an animal is a mammal, then it is a bat. That's not true, right? That is clearly not true. I'm not a bat. I'm not the Batman either. Okay, so you see this distinction between these two things. Isn't this fun math? Okay, anyway. I think we're almost done with 1.3. Yes, let me talk about logical connectives as bit operations. Okay, so well, I'll talk about binary in just a few minutes, but I mean, computers use binary. There are tons of reasons for this. The reason number one is a technical reason. To build circuits that work well, the simplest way to make them work is to have two different voltages. So you can stabilize at a high voltage or a low voltage. So that's two different values, which we call 0 and 1, which we could call false and true also. People have tried to build computers using more than two values. They are technically very difficult to maintain. Okay, so there's no advantage. Okay. Okay, so if you interpret 1 as true and 0 as false, you can reinterpret the basic connectives that we've seen in terms of zeros and ones and just see what happens. Okay, so we just rewrite everything that we did with true and false, and we rewrite them with zeros and ones. Okay, so the not, what does it do? It flips 0 to 1, 1 to 0, obviously. What does OR do? Right? The OR is always true as long as one of the first two is true. So this will be 1 as long as there's a 1, X or Y is 1, otherwise it's 0. What is the AND? The AND is 1 or true if both are true, 1, otherwise it's 0. The XOR you see is 1 when exactly one of them is 1. Okay, so obviously we haven't learned anything, right? We just erased true and false and put zeros and ones in terms in their place. But it turns out that if you think of 0 and 1, 0 being less than 1, you'll see the following thing happen. Well, first of all, AND is the same as multiplying or the same as the minimum value. So let me go back. Sorry, I'm flashing my slides in your face, but let's look at AND here. If you multiply 0 and 0, you get 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. Isn't that cool? So AND is the same as multiplying. Okay. Or you can view it as minimum value. If you have two inputs, X and Y, you take the minimum of these two values, this is what you're going to get. OR is the maximum. Okay, OR is max. XOR, it's a kind of plus. I mean, if you do math next year, you'll do linear algebra, and you might know you'll do linear algebra on reals or complex numbers. But you can do linear algebra on other kinds of fields. You can do it on the two-element field, and you'll see that this XOR is actually the plus. But that's why it's a plus with a circle. But for now, just see it as parity of the sum. Okay, so what do I mean by that is look at the sum. 0 plus 0 is 0, that is even. 0 is even. 0 plus 1 is 1, 1 is odd. 1 plus 0 is 1, 1 is odd, that's 1. 1 plus 1 is 2, which is even, and you get a 0. Okay, so that's what you can actually, you know what, in 3 weeks we're going to see that this is just plus. I mean, yeah, I forgot, that's true. Yes, I'm going to do that for you guys. That's good. Okay, so that's the definition of, or the reinterpretation of and or not XOR in on bits. You can also use these on bit strings. So if the input is a bit string rather than just a single bit, you can apply these operations on these bit strings just coordinate wise. Okay, so here your inputs are 2-bit strings like this, and you apply these operations, these connectives on these bit strings. So the OR, you apply 0 or 1 is 1, 1 or 1 is 1, and so on. You just apply coordinate wise like that. Okay, so you can input bit strings into these things, and you output a new bit string. Okay, so I'm mentioning, I'm mentioning this because it's fundamental, but also because you'll have some examples in the exercises. Will deal with these things a little bit. Okay, you know what? I'll keep the completeness for next time because I don't want your brain to explode. And so I'm gonna go to my other set of slides for something a little easier, a little lighter. Let's do that. What is that? I don't want that. Let's go here. Okay. Okay, do you guys see this? Yeah, number systems, yeah.
Yep.
Okay, so what I want to do is go through very briefly the basic number systems that you already know, might know, and should know. Okay, and I'm just going to try to also connect to what we've been doing up to this point a little bit. Okay, so this is very brief. This I'm going really sort of quickly over the basic number systems which are related to computer science. So the decimal number system is the human number system. Okay, very probably because most of us have 10 fingers, but that's the one that almost all humans use today and have been using for a while. But computers use binary, and like I said, the very main reason, that's not good English. The main reason is a technical one. I mean, building computers with 2 values it's the easiest from a technical point of view. But it turns out also because you have these 2 values, 0, 1, true, false, you can do logic. Yeah, okay. What about octal and hex? Octal and hex are, this is binary for humans. That's basically what they are, okay? Now, unfortunately, we use the same digits or some of the same digits for decimal, octal, binary, and all that. So sometimes you write down a number and it's not clear if you're talking about these things in which base it is written down. So the notation, the standard notation is to write a little index with the base. So if it's octal, you have a little 8. If it's hex, a little 16. If it's binary, you have a little 2. And for decimal, we'll just won't write it, okay? So let me review. Decimal. in one slide. Okay, so the decimal number system is a way to write down numbers. Okay, it is a positional system, which means that the position of a symbol changes the value of what this digit represents, right? What are the symbols that are used to write down numbers? They're called the digits. There are 10 of them. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's their names. Okay. 10 is the base. Okay. Which means that the positions or powers of 10, right? So the rightmost position, this is confusing, right? That's my right. That's your right. Anyway, that's the position of the units, right? So 10 power 0. And if you move left, yeah, this way, the exponent of the base goes up by 1 by each step that you move left, okay? So for example, if you write in decimal 7, 2, 3, 4, this sequence of symbols, which number does it represent? It represents the number 7 times 10 power 3, plus 2 times 10 power 2, plus 3 times 10 power 1, plus 4 times 10 power 0. Hopefully, everybody is good with that. Yes? Yes. Okay.
Yes.
Yes, excellent. All right. So now I'm a lazy kind of guy. So what I did is I just copy pasted this slide 4 times. So this is the octal number system. It is a method to write down numbers. Okay. It is a positional system. The position of a symbol is an expression, and an expression changes the value it represents. Okay. There are 8 symbols, which we call the octal digits, which are 0, 1, 2, 3, 4, 5, 6, 7. The base is 8. The rightmost position represents units. So this has value 8 power 0. And when you move left by 1 position, you increase the exponent of the base by 1. So you see my point here. My point is that this is exactly the same thing as base 10, except it's base 8. That sounds silly, but that's what it is. Okay, so if I write 7, 2, 3, 4, I put a little 8 here to indicate that I'm writing this in base 8, an octal. Okay, what number does this represent? It is 7 times the base 8 power 3, because I'm in the 4th position. I've moved 3 times to the left, plus 2 times 8 power 2, plus 3 times 8 power 1, plus 4 times 8 power 0. Notice this is written in standard decimal. So one of the very confusing things about all this is, of course, that we use decimal to write down numbers, right? When we're talking. But so yeah, let me get to your question just a sec. No. What was I? Yeah, wait, what was I saying? Yeah, so we're writing decimals to communicate, right? So if we're talking about decimal, writing in decimal, we're using what we're talking about. It can get a little confusing, but let's not try to think about that too much. Okay. Yeah, Jacob, 7000, that would be, so the little 8 after the bracket means base 8. Okay, so 7000 would be 7 times 8 power 3. There shouldn't be a 10 there. There's no 10s. Right, it's 7 times 8 power 3. Does that?
Yeah, it's just it's kind of hard to write on Zoom with this kind of
Yeah,
notation. The parentheses with the 8 afterwards is supposed to denote 10.
Yes. Okay, yes. Actually, then Wait, but well, then I'm not sure what that.
Since if you write 1 0 as in the
Yeah.
octal number
When
system, it would
yes,
be
okay,
8.
okay. So yes, but you see where this is going.
Yeah, it's
gonna-
confusing. It's
yeah,
confusing.
that's just like super confusing. Yes, absolutely. Yeah. Okay. Oh, I just switched to binary. Okay. So again, copy pasted the whole thing. So binary number system is a method to write down numbers. It's a positional system. It's the same thing, right? It's base 2. There are 2 symbols, the binary digits or bits for short, 0 and 1. Okay. The rightmost position represents units. That's value 2 power 0. You move left by 1 position, you increase the exponent by 1 each time. Okay. So here's an example, 11011 in base 2. This is, so let's just, we have a tendency to write from the highest exponent first. I think comes from polynomials, which is a bit annoying because I have to backtrack 0, 1, 2, 3, 4. Yeah, so this one here is worth 2 power 4. The next one is worth 2 power 3. Then it's 0 times 2 power 2 plus 1 times 2 power 1 plus 1 times 2 power 0. You see, I didn't write the answer in decimal. I just expanded it. Sorry. The Mac mouse has advantages and also disadvantages. I'm still trying to like it. I'm not sure. Hopefully up to now, this sort of makes sense. Okay, base 10, base 8, base 2, same way of writing numbers, except the base changes. I notice I didn't talk about fractions. It's okay, like some other time. But it's the same thing. It's just negative exponents. But let's not go there right now. So let's go to hex. It's the same thing. There's only one slight difference. It's a base bigger than 10. And so we need more than 10 symbols. So we have to introduce extra digits. That's the only difference. So what we do, and this is a convention, is that for the symbols that represent 10, 11, 12, 13, 14, 15, we use the capital letters A, B, C, D, E, F. In the 50s, I mean, this is a standard, I think it was introduced by IBM in 58 or something like that. But that's the one we use, okay? So there are 16 symbols, the hex digits, 0, 1, 2, 3, 4, 5, 6, 7, 9, A, B, C, D, E, F, capital letters, which represent the values 10, 11, 12, 13, 14, 15, okay? And the way to write numbers is exactly the same. So here, if I write DECAF in hex, hexadecimal, base 16, what does it represent? 0, 1, 2, 3, 4. So D is 13 times the base 16 power 4, because we are in the 5th position from the going left, plus E, which represents 14. You see here I'm using decimal to write down my numbers, times 16 cubed plus 12 times 16 squared, and so on and so forth, okay? And so you see that this will generate a very large decimal number, right? You see that this is going to be pretty big, right? So hex is more compact, right? Obviously. Okay, so here you have decimal, binary, octal, hex. The last couple of things I want to say is conversions between these, okay? So the first thing I want to say, and this is like the justification of when I was saying hex and octal are binary for humans. What I mean is this, is that if you had to, if you had to memorize your address, you probably all know your address, hopefully. But if you had to memorize it in binary, it'd be a lot more painful. Like this long sequence of, especially if you live in the suburbs with this 5-digit address, then you'd have like a very, very long sequence of zeros and ones to remember your address, and that's not good. We're not good at that, right? So so hex and octal are a compromise. So they are very close to binary, but they look like decimals, so they're easier for us to read and memorize or understand than just long sequences of zeros and ones. And so the basic idea is that 8 and 16 are powers of 2. And so, and you should think about this a little bit, because it takes a few minutes or maybe a little bit more to figure it out, but it's not hard, is that if you look at a number written in binary, if you're shifting by 1 to the left, you're multiplying by 2, right? It's the value is twice what it was in the previous column. And so if you move by 3 positions, it's 2 times 2 times 2, 2 power 3 is 8. So shifting by 3 bits is like multiplying by 8, okay? And if it's 4, it's multiplying by 16, right? Because 2 power 3, 2 power 4 are 8 and 16. And so if you take a binary number and you chop it up at every, let's say, 3 bits, when you're looking at the next 3 bits, if you just forget that they've been shifted, you get a number which inside the big sequence of bits is 8 times more. And if you shift another 3, it's 8 times 8 times more, and so on, just like octal, right? So basically each group of 3 bits is an octal digit. So you can rewrite your sequence of bits by regrouping in 3 bits as an octal number. If you do it by 4 bits, you're writing it in hex. And so, and you can go back, of course. Okay, so let me show you what I mean by this. Okay, so look at the number 11101 in binary. Okay, and I'm going to just add a 0 in front so that I have groups of 3 bits. Okay, so I have 011 followed by 101. Okay, 011 is 3 in octal. Okay, and well, it's 3, right? And 101 is 5. Okay, so 011 101 is 35 in octal. You just group into groups of 3 bits and replace by the octal digit that corresponds to that. Okay, another example, this time in hex. If you look at the binary number 1011101, I'd like to group in groups of 4, so I'm going to add a 0 in front. Okay, now the first 4 bits, 0101, that's 5. Okay, now to illustrate what I was saying, so these bits here, if you just look at these bits, that's worth 5. But within this number, they've been shifted by 4 to the left, so they're multiplied by 16, right? So 5D, since the other 4 bits, 1101, that's 13, which is D in hex. This number in hex is 5D. But the key point is to understand where the 5 comes from. So it's these 4 bits, but they're shifted by 16, exactly like this, right? 5 shifted by 16, okay? To go in the other direction is even easier, right? So if you look at the number 3AB2 in hex, okay, each one of these digits is a number between 0 and 15, which is 4 bits, okay? And when you shift by 1 in hex, it's like shifting by 4 in binary, 16 all the time. So I can write down each one of these digits using 4 bits. So 3 is 0011. A, which is 10, is 1010 in binary, right? 8 plus 2. B is if you're not used to this, I mean, this might be going a little fast in terms of, whoa, what is, 10 is 1010, or sit down and do the computations. It'll help, but you'll have to do it after. B is 11, which is 1011 in binary, and 2 is 0010, and you just push them together. These sequences of 4 bits, these 4, these 4, 4, and 4. And that's your number in binary. Hence, what I meant by hex is binary for humans, because trying to memorize this is a pain, right? But this is much easier, right? It's more readable for us. Okay. Okay. I think that's all I wanted to do. No, I just, this last, yeah. List of the first few numbers in decimal. Well, that's easy. Okay. The first few numbers in octal. Yeah, so if you start counting in octal, right? 0, 1, 2, 3, 4, 5, 6, 7. The next one is 1, 0. Don't say 10. If you say 10, you're gonna mess up. This is 8, but if you say 8, it's very, very confusing. But you see how this goes, right? So you reach 1, 7 in octal. So then you have 8, so that's one more here, and you keep on going. It's a good exercise, actually, to write down the first few numbers like this by yourselves. Binary, even better. Now, the way they're written here is they don't have, I mean, obviously the number of bits increases. In a computer, the bits are, I mean, the memory slots are fixed, and you fill in the bits. So it's standard to write numbers in binary on, let's say, a fixed number of bits. And so if you look at the first few numbers here, let's say on 4 bits, this is what you get. And what I meant to say, this is important, that if you look, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, right up to 15. Look at them, and they are actually in the alphabetical order, right? So you can generate these without actually interpreting them as numbers. But if you start with all the zeros, then the next one you increase the last bit to 1. Then the next one will be 0010, 0011. Hopefully you see what I mean by alphabetical order, or lexicographic ordering is the oops, sorry. Stupid mouse. Yeah, and by the way, this illustrates something that I said earlier. I'm sorry, this lecture is getting really long. About the power set, right? When I said if you take the subsets of a set with 4 elements, you can see these as bit strings of length 4, with a 1 appearing in a position that indicates that element for that position is in the set. And so these are all the possible bit strings of length 4, and you have 16 of them, right? Because it's 0 to 15 in binary. And the last thing I wanted to say is for truth tables, that was one of the main points of this whole thing, is that if you have a compound expression with n variables, then the truth table will have 2 to the power n rows. So when I said that the algorithm to check if building tables is not efficient, it comes from this exponentiation here. That's the reason. And so how do you list all possibilities? I've done it, all my examples had 2 variables, so we had 4 cases, that was easy. But just to make sure that everybody could do it for 8 or 16, this is the way that you could do it, okay? So if you list all possibilities for the values for your variables, let's say you have 4 variables, then I've listed here all the possible different values for all the 4 variables. what I did, if you look at that and you compare to the numbers from 0 to 15, it's exactly the same thing, right? I just use, rather than zeros and ones, I use true and false, right? So it's the same thing. So hopefully you see the connection there. So if you have to build a truth table, and we'll get back to that on Thursday when I do problems, but if you have to build a truth table, look at the number of variables. If you have 3 variables, then you have 8 rows. But a common mistake that I've seen, and it's a bad mistake to make, is to not list the correct different values for the variables, right? If you repeat some, then you're going to miss some, and it doesn't work, right? So make sure you can actually list all of these correctly. Well, we'll talk about it more in detail on Thursday. Sorry, this was really long. I'm really sorry about this. Any questions, comments at this point?